Bismillahirrahmanirrahim. I am Dr. Asad, Lecturer, Institute of Numerical Sciences, Cohort University of Science and Technology. Dear students, welcome to the course of Fluid Mechanics, course code MATH-361, lecture number 10. In this lecture, we will discuss law of conservation of mass and some other related topics. In the previous lecture, we discussed the material derivative and its derivation on the basis of the infinitesimal fluid element that is flowing from one point to another point in the Cartesian plane. We also performed some exercises by using the Cartesian form of the material derivative, and further we discussed the volumetric flow rate, mass flow rate, and mean velocity. And then we derived the mathematical form for the volumetric flux through a surface, and also performed some exercises by using that mathematical structure. And at the end of that lecture, we provided some exercises for the students as a homework. In outlines, in this lecture we will discuss the following points. Number 1, the law of conservation of mass. So we will provide a statement of the law of conservation of mass that already we studied at the school and college level, and then we relate this law of conservation of mass with the continuity equation that is based on the fluid mechanics. And number 2, the Gauss divergence theorem. So we will provide the statement of the Gauss divergence theorem and also its mathematical form, because we will use the Gauss divergence theorem in the derivation of the continuity equation. Number 3, we provide some basic integrals, that is the surface integral, the line integral, and the volume integral and their relations. Number 4, we will derive the continuity equation, that is the law of conservation of mass. And number 5, there will be some problems on the continuity equation. Number 6, we will establish a relation between the continuity equation and the material derivative. Number 7, there will be some practice problems to the students. And finally, there will be references. Now, what is law of conservation of mass? The law of conservation of mass, or principle of mass conservation, states that for any system close to all transfer of matter and energy, the mass of the system must remain constant over time. I am explaining this law by considering the simple chemical reaction of methane with oxygen. When methane reacts with oxygen, we get carbon dioxide and 2 molecules of water. In the reactants, there is only 1 carbon and 4 hydrogen atoms, while 4 oxygen atoms. Now in the products, there is only 1 carbon, 4 oxygen atoms, and 4 hydrogen atoms. So by this reaction, we see that the number of atoms in the reactants is the same as we get in the products. So the law of conservation of mass holds in this reaction. Now, how to relate the energy and mass of a system? So we use the famous Einstein E is equal to mc square equation. By this equation, we can convert mass into energy and vice versa. Here E is the energy, m is the mass, and c is the speed of light in vacuum. Now, what is the Gauss divergence theorem? You can see the picture of the Carl Friedrich Gauss, who was a German mathematician, who established a relation between the surface integral and the volume integral. In his famous theorem, he states that let R be a simple solid region and S is the boundary surface of R with positive orientation. Let F be a vector field whose components have continuous first order partial derivatives. Then the surface integral of the vector function f in the dot product of the unit normal at the surface S is equal to the volume integral of the divergence of the vector f. So in this mathematical structure, you can see that the surface integral is related to the volume integral, and this relation is most important because we will use this relation in the derivation of the continuity equation. Now, some important integrals. Students are already aware of these integrals because this is already taught to the students at the Calculus 1, Calculus 2 and Calculus 3 courses. Now, the fundamental theorem of calculus is used for finding the area under the curve, in which the base is normally chosen as a straight line. So, by using the fundamental theorem of calculus, we can find area, that is the f of b minus f of a, where b and a are any points on the straight line x. Now, the fundamental theorem of the line integrals, which can be used for any smooth curve. This is the point A, which is any general point, and this is any general point B. So we can integrate from A to B by using the mathematical form of the line integral. Now, number third, this is the Green's theorem, which is in the form of the circulation. So Green's theorem relates the area integral to the closed curve C integral. You can see that g of x shows that the function g is partially differentiated with respect to x, while f of y shows that this function f is partially differentiated with respect to y. And this is equal to the closed curve C integral f dx plus g dy. Now, what is Stokes' theorem? This is the mathematical form of the Stokes' theorem given here. In this theorem, the surface integral of the curl of a vector f into the dot product of the unit normal at that point is equal to the closed path C integral of the vector function f in the dot product of the radius of the curve C. Here you can see that this is the closed curve C in the counterclockwise direction, while this is the whole surface S. So, by Stokes' theorem, we can relate the surface integral and the closed path C integral to each other. Similarly, in the divergence theorem, we can relate the volume integral and the surface integral, in which the divergence of the vector f is equal to the surface integral of the vector function into the dot product of the unit normal at that point. This is already discussed in the first slide in detail with also its mathematical form. Now, what is equation of continuity? Before deriving the continuity equation and discussing the geometry in detail, in the previous lectures we have already discussed that how to derive a basic equation in the fluid mechanics by using different models. So in fluid mechanics, a single equation can be derived in 4 different ways. So there are 4 different models used for the derivation of a single equation. Number first, the finite control volume fixed in space with the fluid moving through it. This is case number 1, in which we consider a finite control volume inside the fluid flow and discuss the fluid behavior at that fixed point. Number 2, the finite control volume moving with the fluid such that the same fluid particles are always in the same control volume. In the second case, we consider a fixed space, that is a fixed surface inside the fluid flow, and consider the motion of that surface as the fluid flow. And we consider the particles inside the space as fixed because the fluid inside the surface and the fluid outside the surface are not allowed. In the third case, we consider an infinitesimal fluid element and discussed the fluid flow from that point that point should be chosen fixed in space, as we discussed. That is the fixed surface inside the fluid flow. So it will be a fixed differential volume, that is fixed infinitesimal fluid element inside the fluid flow. In the fourth case, we consider an infinitesimal fluid element inside the fluid flow and follow its motion throughout the flow. While the infinitesimal fluid element always contains same number of molecules, same number of elements as the fluid flow. Now, to derive the continuity equation, I am considering a closed surface inside the fluid flow that is denoted by S. Here I considered a simple molecule whose volume as dV, and this is a simple surface inside this. This is the small surface ds whose normal vector is denoted by ds, that moves with the velocity v as the fluid passes through this point. Now, the law of conservation of mass can also be stated as that the net mass flow out of control volume through a surface S must be equal to the time rate of decrease of mass inside the control volume. It means that if we have a control volume and the mass is flowing through a surface S, it must be equal to the rate of decrease of the mass inside the control volume. Now, the mass of the fluid within the volume is given by equation number 1. We know that density is equal to mass per unit volume, and so by cross multiplication we get that mass is equal to rho dV. Here dV is the elemental volume, it is volume of each fluid element on the surface S. Now, the time rate of increase of mass inside the surface S is given by equation number 2. We have just taken the local derivative of equation 1 with respect to time. Since the surface is fixed inside the fluid flow, as time passes, the fluid came and passes through the surface. So with respect to time, finding the change in mass, which is given by equation number 2. This is the local rate of change, because the surface is fixed inside the fluid flow, so that's why we did not use the material derivative. Now, the inward mass flux into the surface S is given by equation number 3. This equation is proved in the previous lecture. Its detailed derivation is given in the last lecture. The negative sign shows the direction of the flux, where v is the velocity vector and n is the unit normal to the surface S and rho is the density. Now, the principle of conservation of mass requires equation number 3. What equation number 3 shows? Equation number 3 shows that the inward mass flux must be equal to the time rate of change of mass inside the closed surface. So, to transform the surface integral to the volume integral, we use the Gauss divergence theorem. So, the surface integral is equal to the volume integral, that is the divergence of the density times the vector function v. So, in equation number 3, we match the surface integral to the volume integral by using the famous Gauss divergence theorem. Now, using equation 3 in equation 4, we get the result in the form of equation star. Now, moving the left side to the right hand side, we get the result in the form of equation double star. Here, in this derivation, we considered the closed surface S, which is continuous and differentiable. So, in equation double star, the integrand must be equal to 0. So we get the result in the form of equation 5. This equation 5 is the continuity equation, which is the mathematical form of the law of conservation of mass. Now some special cases. In case number 1, if the fluid flow is steady, then equation number 5 can be written in the form of equation A. A flow is said to be steady if every fluid property remains constant throughout the flow. So the derivative with respect to time will be equal to 0. So the density with respect to time derivative will be equal to 0. So we get equation number A from equation number 5. Now in case 2, if the fluid is incompressible, then equation 5 can be written in the form of equation B. Incompressible fluid means that the density of the fluid is constant. So the derivative of the density with respect to time will be equal to 0, and similarly we can also common out the density from this relation. So we get just the result in the form of equation B. Now to understand the use of equation of continuity, here I am presenting a simple example. Here show that u, v and w are the velocity components of possible incompressible fluid flow. Is the flow irrotational? In this example, we have to check whether the velocity components u, v and w satisfy the equation of continuity for the incompressible fluid flow. If it satisfies the equation of continuity, then the fluid flow is said to be possible. In the second case, we have to check whether the fluid flow is rotational or irrotational. Now, in solution, for an incompressible fluid flow, the equation of continuity is given by equation number 6. Now, to calculate partial u over partial x, partial v over partial y, and partial w over partial z, we get the first velocity component, that is the derivative of u with respect to x, is given by equation number 7. Now the remaining two components, that is the derivative of the velocity component v, is given by equation number 8 with respect to y, and the derivative of the velocity component w with respect to z is given by equation number 9, which is equal to 0. So using equation number 7, 8 and 9 in equation number 6, we get the result in the form of the satisfied continuity equation. That is, the left hand side is equal to 0 and the right hand side is also equal to 0. So equation of continuity is satisfied identically. It means that the fluid flow is possible. Now the flow is said to be irrotational if curl of a vector v is equal to the 0 vector. Now using the definition of the curl, we get the following determinant, that is the result in the form of 3 cross 3 determinant. This determinant is equal to 0 by expanding any column or any row. So we get curl v is equal to 0. So the flow is irrotational. Now, what is the relation between the continuity equation and the material derivative? Since equation number 5 is the basic continuity equation, so using the dot product of the nebula operator over the scalar multiple of a vector, we get the result in the form of equation number 10. Now, we know that material derivative is defined to be in the form of equation number 11. So using equation number 11 in equation number 10, that is this part will be replaced with the material derivative, and we get the result in the form of equation number 12. Now equation number 12 shows the relation between the continuity equation and the material derivative. Practice problems. Students are advised to solve problem number 1 and problem number 2 as their homework. If they feel any problem, they can contact me on my email address given at the footnote. Now in problem number 3, relate the continuity equation A1V1 is equal to A2V2 of the fluid flowing through a pipe of different cross-sectional area A1 and A2 to the continuity equation we discussed in this lecture. Finally, in references, all the materials in this lecture are provided from the following references. And in conclusion to this lecture, in this lecture we stated the law of conservation of mass and the gas divergence theorem, and further we provided some basic integrals and proved the law of conservation of mass, that is the continuity equation, and then we established the relation between the continuity equation and the material derivative. And finally, we provided some practice problems to the students.